All right. So let's jump right in. You're going to need your periodic table. You're also going to need the list of polyatomics, which I'll go ahead and upload into the chat now. Uh, so go ahead and open that up. It's there. It's a PDF document. If you're on your phone, you're not going to be able to see it. But if you go to Blackboard, you can grab it from Blackboard. So we're going to take this first problem, and what we're going to do is basically deconstruct these examples. As it says, the following ionic compounds are found in common household products. Write the formulas for each compound. We're going to do something in addition to that. We're not just going to write the formulas. We're also going to break these things apart into their components. So each compound is made up of a cation and an anion because it's anionic. I mean, it's ionic. I'm sorry. So with that, let's look at the first uh, example, and it's asking us to write the formula for potassium phosphate. So you're going to need a couple of things. You're going to need the atomic symbols. You're going to need the charges. And you need your polyatomics. All right, you're going to have those things in order to convert a name into a formula. And in order to do that, you can get your atomic symbols from the periodic table, but the polyatomics, you're going to have to familiarize yourself with that list. On the exam, feel free to use the list. It's the same. It's the same format as the first exam. It's hosting on Blackboard. It's not proctored or locked down or anything like that. But as we go forward, you're going to be expected to be less and less dependent on that. So you need to familiarize yourself with those polyatomics. So make sure, go ahead and open that document up. And if you have a periodic table close by, you can open that document up. And let's go ahead and knock this out. So can somebody tell me what the symbol for potassium is, as well as the group number? Because with the group number, we can determine its charge. Anybody? So if you look at the periodic table, all the way to the left under sodium, you should see potassium. Okay, all right. So the symbol for potassium is K, right? Not PO, not PT, not PS, PM, nothing. It's K, right? We talked about some of these elements having odd symbols. And thank you, Nazir. It's in group 1, right? So that means that and because it's a metal, this is something that we need to commit to memory. That metals are cations. They are able to give away electrons and become cations. That's partly due to their electronegativity. They are not very electronegative, so they lose electrons readily. We'll talk about electronegativity later. Uh, but potassium is group 1, so that means it's going to have a +1 charge. All right. And then with the phosphate, can somebody look up the phosphate polyatomic? This is a polyatomic. It does not have a periodic symbol because it's made up of multiple elements. It's made up of both phosphorus and oxygen. So you will not find that on the periodic table, but we do have a list of polyatomics that we can learn. And we also need, when we're dealing with these polyatomics, we need the charge, because the charge is going to determine the ratios of the elements. Anybody got it yet? Phosphate. Scroll down on that list and find it real quick. All right, let's see. Okay, PO4, good. Nausea and okay. And Mary, thank you, is PO4. And the charge is -3. It's very important because, and I'm going to introduce you to a concept that we'll talk a lot about later as we go on. But it's, again, why make you wait when I can talk about it now? So PO4 looks like this. So the way that we would construct the formula for this is to use, we talked about this before, the crisscross method. So we're going to take this number and put it here. Keep in mind, this whole thing is PO4. So any number that I put, I have to put that in parentheses. I'm putting it here, even though it's going to be understood to be 1, right? And then this number is coming here. All right, let me ask you this question. Why is it that I need to put those numbers there? And I'll show you. I'm going to show you why. But the way that this is set up, this is, once we crisscross these charges, this becomes K3. And I'm gonna put this in parentheses. You don't have to, because the number here is understood to be 1, and you don't show that. But what this is saying is that for potassium phosphate, this is what the phosphate ion looks like. It's here. Got 3 negatively charged oxygens on it. With 3 lone pairs. Each one has 3 lone pairs. So there are 3 positively charged potassium ions to neutralize that, right? Because the overall, the compound itself is neutral, right? So K3PO4 means that for every 1 phosphate, there are 3 potassium ions that neutralize it and that make it overall neutral. So every one of these, you'll have a potassium associated with every oxygen, because every one of the oxygens in here, well, 3 of them out of 4 are negative. All right, and then the other part to this, with the ratio of 3 to 1, the other part to this is that everything in chemistry, and I'm giving chemicals and atoms human properties, and I know a lot of scientists don't like that, but it helps us to understand it. But everything in chemistry desires to be neutral. Being neutral is good, right? It's a state of stability, right? So every one of these has a potassium associated with it, and this is an ionic compound, which means what? What does it mean when we say it's ionic? And when we say it's ionic, what is that in contrast with? Because if it's not ionic, then there's another term that we use. Okay, good. It's an attraction. Thank you, Mary. It's an attraction rather than a bond, right? Kind of like Velcro, right? Or like, you take 2 pieces of Velcro, you got the fuzzy side and you have the coarse side. It's just like that. All right. So with potassium phosphate, it is K3PO4. And we don't need this 1 down here because that's understood. Right. So these subscripts point to something, though. They give us a glimpse into another concept, which we call stoichiometry, right? So we're going to talk a lot about stoichiometry later, but it's really dealing with ratios of either compounds relative to one another, or in this case, we could talk about the ratios of atoms in this compound. So I'm going to leave this definition right here, just ratios. Just think about ratios. And here we could say that the ratio of potassium to the phosphate anion is 3 to 1. All right. All right. Any questions so far? We're going to deconstruct all of these names, and we're also going to, do the same thing for each one of these examples. And then I'm going to break y'all out into groups. And we're going to work through the second set of examples. All right, let's go ahead.
Can you put the recitation hand sheet or handout back in the chat?
Hold up.
My fault. My laptop had deleted out my files.
All right, it's there. You should be able to download it now. All right, let's do the next one, which is we got a couple of concepts here we can play with. This is copper 2 sulfate. All right, what is that 2, that Roman numeral 2 that comes after copper? What does that mean? We talked about it the other day. What does that 2 represent?
Is it how many protons?
No, not in this case. Not in this case. So the Roman numeral 2, when you see that after a metal, that means that the metal has more than one oxidation state. So this represents the oxidation state of the metal. So copper just happens to exist as copper 2 plus and copper 1 plus. So it can exist in both of those oxidation states. So can somebody look up the sulfate anion for me and tell me what that looks like, or not what it looks like, but what the formula is for it? Because we know that copper 2, that's telling us that copper is 2 plus. If you look on that sheet with the polyatomics, the sulfate should be on the first page, I think. Anybody got it yet? And the charge. We need the charge as well as the formula. All right. Bet. Thank you, Mary. SO4 minus 2. Keep in mind, this is a unit. This is one thing, right? So we don't break those atoms apart. The SO4 looks like this. All right. And we can write the formula for this. Like we can just write it. But I'm actually we're gonna go ahead and crisscross it up because I want to make a point by crisscrossing it. All right, so the 2's are gonna be here. So this is gonna be a 2 here. And then this is in parentheses. I'm gonna put a 2 there. Right, but that's not really accurate because both of those are 2. So we can just take that down and just write, like you wouldn't write it like with the 2's as subscripts. If both of them are 2's, right? You don't need that because we can reduce that down and divide both of them by 2 and get 1 and 1. So yeah, so with the copper 2 sulfate, we see that there's 1 copper per sulfate. Now I'm gonna show you how this looks because this is it's gonna make what's called a complex. So I'm gonna write this sulfate. I'm gonna change the structure of it. All right, so actually I'm gonna make it look like this. So this will make more sense. So with that sulfate, if you notice now, if you look at the ratio, sulfate has a -2 charge, but copper has a +2 charge. And what that means is that copper can accommodate two bonds, I'm putting bonds in quotes, to the sulfate. And so this is actually going to make a complex that kind of looks like this. So it'll be S double bond O, double bond O, and then O, O with a copper between them, like that. All right, and this bond, you'll talk more about this when you get to CHEM 2, but you'll have a leg up. This is what we call a dative bond. Right, so the oxygen is supplying electrons to copper. Right, so it'll make this type of complex, but that explains the ratio, right? That they're 1 to 1, even though the sulfate has a -2 charge. So you would think under normal circumstances, well, I need 2 coppers to satisfy that, but you really don't. You really can it'll just make a complex like that. All right. Now, what if I had copper 1 sulfate? How would I draw that? Again, the 1 in parentheses, the Roman numeral, is indicative of the oxidation state of the metal. So how would I write out copper 1 sulfate? What does that tell me about the oxidation state for copper? Is it +1 or +2? Let's see if this is a Roman numeral 1, that means this is +1. And then the sulfate, SO4 minus 2, we already know. And this is all in parentheses because it's one group. So if we just crisscross these charges like so, put this here, put the 1 here, we end up with Cu, right? And then 2 SO4. Remember, this is understood to be 1, so we don't have to write it. Cu2. Now, that would indeed have 2 coppers, right? So you'll have, for that sulfate, it would look like this. Sorry about that. So that's Cu plus and then Cu plus, like that. All right, so both oxygens are negative, and then you have, if you look at the ratio, there are 2 coppers for every 1 sulfate, so it has to look like what we have shown. Any questions? Any questions about anything? All right, let's go and do the next one. Calcium chloride. Can somebody tell me what group calcium is in? Look at the periodic table, start at the left, work your way over. You're going to run right into it. Feel free to put it either. Okay, good. Group 2. So if calcium, which is a metal, is in group 2, what that means is that calcium is going to have a +2 charge. All right, good. And then the chloride, that's a halogen over in group 7 in the non-metal section. Right, so we're going to write that like this, Cl, and we're going to make that -1. Right, so group 7 atoms have a -1 charge, and then group 6 atoms, which is like oxygen, sulfur, those atoms in that group have a -2 charge. I'm saying that because we're going to come to a problem like that in a second. All right, so again, we take this, we crisscross them over like that, and we get CaCl2. Right, calcium chloride is a highly insoluble white solid and is used as a desiccant. You can add it to something that contains water, and it will absorb the water from a solvent. It's a way to one way to dry solvents is to use calcium chloride. But it's really messy to work with because it's very powdery. So you always end up having to filter your stuff more than once. Right. So again, this is an ionic compound, and every 1 calcium, since it's 2+, is going to have 2 chlorines bound to it. Right. Let's do the next one. Titanium. I think yeah, titanium 4 oxide. What does the 4 on titanium 4 oxide mean? That Roman numeral. What does it mean for titanium itself? There's a Roman numeral 4 in parentheses following a metal. What does that mean? We just saw it with copper up top, and now we're seeing it again.
Can you repeat the question?
What does that Roman numeral 4 indicate?
Didn't you say the oxidation state or something like that?
The oxidation state of titanium. Exactly. So titanium is Ti, and the 4 means it's going to be in the +4 oxidation state. It's a transition metal. So transition metals often have multiple oxidation states. They can be, they can exist in, multiple forms based on how many electrons they're able to give away and become cations. But this is titanium +4. The oxide is O -2, right? And so again, same thing. And I'm repeating this so many times because I'm about to put y'all in groups, so you'll be doing it on your own. So this is here, crisscross them up. All right, so it's Ti2O4, right? And you may think that this is weird, but it's really not. This is when you have a 2 here like this. This is often indicative of what we call a biometallic complex. All that means is that there are, yes, great question, Mary. You can, so this is I talked about that this morning as well. This is the molecular formula. And then if we were to write this as the empirical formula, we would simplify it down. It would be TiO2. Great question. Great question. Yep. So the empirical formula would be TiO2. The molecular formula is what it is. All right. So the way that a complex like this would look, you basically would have a bond between 2 titanium atoms. So titanium would look like that. And then 2 oxygens on each one. Right. So Ti2O4. And there more than likely there's going to be a bond here between the oxygens as well, just to satisfy the octet. We haven't talked about octets yet, but we will. But yeah, so, and plus oxygen is a diatomic, so it's going to be O2 anyway. In its elemental form, it's a diatomic. So probably the complex would probably look something like what's there. And there's actually a bond between the 2 titanium. So we call that a biometallic complex. All right, let's look at, what's the next one? Keep scrolling back up. Ammonium nitrate. This is a good one. Because both of these are on that list of polyatomics. All right, so ammonium nitrate. Somebody tell me what the symbol or the symbol is for the ammonium ion. It's a cation. And then what about, and somebody tell me what the symbol is for the nitrate. Anybody? Okay, let me see. Okay, good. NH4 plus. This is NH4 plus. And then what about nitrate? NO3 -1. So +1 -1. So when I was talking to the class this morning, I made a point to say that if the numbers here were identical, but just opposite charges, you can kind of skip past the crisscross part and just write this out. All right, so if your numbers are identical, but opposite charges, just write it out what you see. If you wanted to crisscross them, you could, but both subscripts are going to be 1, and it's already reduced to its lowest form, and you don't have to show it if it's 1. It's understood. All right, so when those two numbers are the same but different charges, you can just cancel them out and bring the two together. All right. Any questions about that? All right, let's do the last one, and I'm gonna sodium bisulfate. All right, so can somebody look up the bisulfate polyatomic? And then somebody tell me what the symbol for sodium is. It's in group 1. And it's not SO or SD or SM. It's one of those elements that we talked about before. Good, thank you. It's Na, and it's in group 1, so it's going to have a +1 charge. And then the bisulfate, what does that look like? Or what's the symbol for it based on that table with the polyatomics on it? All right, so it's the sulfate, so it's going to be a SO4 something, yeah. And then how many hydrogens? Because if you look at the table, it gives you all the sulfates. So it's HSO4 and has a -1 charge. So let me show you. We've seen what SO4 looks like, right? So it's here. So that H is here. This oxygen has a -1 formal charge. So that's what that looks like. So that's how it's HSO4. And so the actual compound would be ionic, where sodium is just hanging out where that negatively charged oxygen is. All right, it's attracted to that charge. But when we write this is -1. Again, the charges are the same, the numbers are the same, but the charges are different. So this becomes NaHSO4. All right. If you want to Google the uses of these different compounds, because it said that they're found in common household products, by all means do so. You'll be surprised that titanium oxide is used in toothpaste. Ammonium nitrate is used in a lot of cleaning products. The calcium chloride, the same. Copper sulfate. You'll be shocked at some of the common commercial uses of these compounds. All right. So with that being said, we're going to take this other question. I'm going to cut it and paste it at the bottom. And I'm going to break y'all up into groups. Where's that second question? Right here. And when we come, I'm going to do this for probably about 8 minutes. And then when we come back, we're going to talk about each one of these, and each group is, I just randomly ask each group to answer one of these. Let me see how many people we got. 18. Perfect. So I'm going to we got 6 problems. I'm going to do 6 groups, 3 people per group. Let me pause record. E group, we already did 4. So group room 5. Tell us what E is. It's Christine, Naja, or Nazir.
It's I think I'm not 100% sure, but I believe it's sodium nitrite.
Okay, sodium. You see that nitrite?
Yes.
Very, very good. That ending on the nitrite is important. You see how right here is NO2, that's nitrite, and then NO3 would be nitrate. So this is Na plus and then NO2 minus. Both numbers are the same, so we can just put them together. All right. The last one, I'll do it. It's the easiest one on here. It's potassium iodide. Right, so we had calcium dihydrogen phosphate for the first one, iron sulfate, iron 2 sulfate for the second one, calcium carbonate for the third one, magnesium oxide for D, sodium nitrite for E, and potassium iodide for F. Yes, FeSO4. Yes, it's iron 2.
You wrote phosphate.
Oh, did I put phosphate? Oh, my bad. Thank you for catching that. I appreciate it. Iron 2 sulfate. My bad. All right. Any questions about anything? Think this is good. For tomorrow, since the test is going to be Friday, we won't have a new worksheet. And I'll give you the same option that I gave the morning class. If you need more practice, you can show up tomorrow at 1. If you feel confident about this and you don't need any more practice, you don't have to come tomorrow. It's up to you. But I'm going to be logged in at 1 o'clock. So if you need more practice and you have questions, just log in and we'll take it from there. All right. Any questions?